what if the exact process that makes an AI assistant so, incredibly helpful, polite, and articulate is the exact same process that makes it dangerously deceptive when it hallucinates a vulnerability into your code base?
Yeah, I mean, it's the ultimate paradox of the helpful interface. And it all stems from one highly specific, deeply misunderstood phase in the AI training pipeline.
Picture this. It is 2 a.m. You're staring at your monitor. The dark theme of your IDE is the only thing lighting up the room. And your coffee went cold about 3 hours ago.
We've all been there.
Right. You are in the zone, deep into a focused coding session, integrating a large language model into your newest application. You, the software engineer listening to this right now, interact with these models every single day.
You send an API call, you get a helpful response back, and you just use it to build.
Exactly. But tonight, we are looking at the mechanics behind how that actually works. We're doing a deep dive into instruction tuning. Okay, let's unpack this.
It really is the unseen bridge in the development cycle. Without it, the user experience you just described, well, it simply wouldn't exist. You'd be building on top of total chaos.
Because a raw-based model, straight out of its massive initial pre-training phase, is not a helpful assistant. It's a massive autocomplete engine.
Right. It is an algorithm that is strictly trying to minimize cross-entropy loss over a gigantic corpus of internet text.
So if you prompt a raw base model with a question like, how do I reverse an array in JavaScript? It might not give you the code.
No, it might just output, how do I reverse an array in Python? Followed by, how do I reverse an array in C++ Dama?
Which makes perfect sense if you think about its initial objective function. I mean, it spent months on a GPU cluster reading Stack Overflow and Reddit.
Yeah, exactly. When it sees your question, it doesn't recognize a user seeking an answer. It recognizes the start of a forum thread compiling a list of programming questions.
It just wants to finish this statistical pattern. So as developers, we have this massive pre-trained neural network with an incredible latent space of knowledge. It knows the syntax of 100 languages.
But it has absolutely no concept of API endpoint routing. It doesn't know how to route your prompt to a helpful response.
So how do we physically alter the model to bridge that gap?
We do it by fundamentally shifting its objective through fine-tuning, specifically on instruction and response pairs.
Okay, so we take that raw model and feed it highly structured data.
Right. The input is a clear imperative, like write a Python script to sort a list, and the target output is the exact correct response.
Under the hood, we're doing a supervised fine-tuning pass, right?
Yeah.
But often we mask the loss on the prompt tokens.
Yes, exactly. The model is only penalized for getting the response wrong.
So we are teaching it a new structural format. We're telling it, stop trying to predict the next word of an internet document and start predicting the next word of a helpful answer to this specific command.
And that introduces a massive engineering challenge. Because once you establish that you need instruction response pairs to build this bridge.
The immediate architectural question is, what kind of data do you use?
Right. If you want an AI that can code, do you only train it on coding instructions? If you want it to write emails, do you only use email pairs?
Which brings us to the LLM recipe. This is a massive milestone in the research we're looking at tonight, and it completely reframes how we think about training datasets.
The researchers behind LLM proved that the diversity of the tasks you use for instruction tuning matters immensely more than just focusing on your target domain.
They didn't narrow their focus.
Not at all. Instead, they took over 1,800 existing traditional natural language processing datasets, things like translation, sentiment analysis, document classification.
And they reformulated them into an instruction format. Let's break down that reformulation, because that's the really clever part.
Yeah, so they took a classic sentiment analysis dataset, which is usually just a CSV file with a review and a positive or negative label.
Right. And instead of feeding that raw data in, they wrapped it in a natural language template. Like, read this movie review and tell me if the sentiment is positive or negative.
They did that across 1,800 uniquely different NLP tasks. They created a massive mosaic of operations.
Summarize this, to translate that, extract the entities from this paragraph.
Exactly. And what's fascinating here is the real aha moment of the LLM recipe, demonstrating zero-shot transfer learning.
Right.
By training the model on this massive variety of tasks, it gained a general instruction following capability that transferred to completely unseen tasks.
Okay, wait, hold on. I have to put my software engineer hat on here because that sounds like magic, and we know code isn't magic.
Yeah, fair enough.
If I write a massive switch statement in my backend with 1,800 specific cases, and a user hits case 1,801, My program throws an unhandled exception. It fails.
Yeah, of course.
It doesn't magically infer what to do. So how is the neural network surviving case 1801 without just being a giant lookup table of memorized patterns?
Well, it survives because the architecture of a transformer network doesn't actually work like a rigid switch statement. It's doing something far deeper than rote memorization.
Okay.
Because it is exposed to 1,800 entirely different ways of being asked to process text, the model is forced to abstract the underlying relationship between a command and its execution.
So it learns a meta skill.
Yes, it learns the concept of an instruction itself. It learns that when a sequence begins with an imperative verb, followed by some context, its job is to perform an operation on that context and map it to an output.
It's not memorizing the answer to task 45.
Exactly. It is internalizing the mathematical vector representation of helpfulness and compliance.
Man, that resonates perfectly. It's exactly like learning a programming paradigm rather than memorizing syntax.
That's a great way to put it.
Once you deeply understand the principles of object-oriented programming in Java, you can pick up C# incredibly fast. You aren't starting from zero.
Right. You understand the meta skill of classes, inheritance, encapsulation. You just need to apply it to a new context.
And that generalized representation prevents the model from overfitting to any single type of request.
Diversity acts as a regularizer. It forces the model to be adaptable.
But wait, if LLM used 1,800 massive datasets to teach this meta skill, well, the natural assumption for anyone in machine learning is that volume is everything.
Oh, absolutely. The core dogma of the big data era.
Right. The idea that if 1,800 tasks give you a good model, then a billion tasks must give you a flawless one. Throw more compute at it, shovel in terabytes of data.
The standard playbook.
Is that massive volume actually a hard requirement or just an artifact of early research?
It turns out it's a massive fallacy, and that leads us directly to a fascinating study called LLM.
Oh, yeah.
LLM stands for less is more for alignment. It challenges the more data is better philosophy right at its foundation.
Lima really stops you in your tracks. They produced a highly capable, instruction-tuned model using only 1,000 examples.
Just 1,000.
Not a million, not a billion. Just 1,000 carefully curated instruction and response pairs.
To understand why that works, we have to look at what the Lima researchers call the superficial alignment hypothesis. It's a brilliant concept.
Let's get into it.
The hypothesis states that a model's actual knowledge and core capabilities are learned almost entirely during the massive pre-training phase.
All those months on the GPU cluster reading the internet.
Yes. That's where it learned how to code, how to reason, and how to understand physics. Instruction tuning doesn't teach it how to do those things.
It just teaches it the style or format for interacting with users.
Exactly. It's a stylistic wrapper, which means you don't need a billion examples to teach style.
If you just need to teach it the format of a helpful assistant, a very small number of beautifully crafted examples can entirely outperform massive, noisy datasets.
The researchers behind Lima meticulously handcrafted those 1,000 examples. The tone was perfect, the formatting was flawless, the logic was sound, and the helpfulness was dialed up to the maximum.
It's the exact same principle as code-based maintenance.
How so?
Well, 1,000 lines of beautifully optimized, handcrafted, deeply reviewed code will execute and scale infinitely better than a million lines of bloated, copy-pasted, unreviewed spaghetti code.
Oh, absolutely.
The bloated code might eventually compile, but it's inefficient, unpredictable, and prone to massive edge case failures. If you feed an AI a million low-quality, scraped-from-the-internet examples, it learns to mimic that noise.
It learns to be a mediocre assistant.
Right.
But let's add some friction here because Lima isn't a magic shortcut. When we say 1,000 perfect examples, we're talking about weeks, sometimes months, of grueling labor by highly paid domain experts and PhDs.
Yeah, that's a good point.
Writing a truly flawless instruction-response pair for a complex coding problem, verifying the syntax, ensuring the explanation is pedagogically perfect, formatting the markdown, it takes significant human time.
Right. It's an intense quality assurance bottleneck. It shifts the problem from a compute bottleneck needing massive server farms to process billions of rows to a human labor bottleneck.
Which is still a massive barrier to entry. I mean, if you are a small engineering team or an indie developer trying to fine-tune an open source model for your specific use case, you probably don't have the budget to hire a team of domain experts to spend a month writing pristine training data.
So how do we bypass that? If human labor is the bottleneck for high-quality data, how is the open-source community suddenly releasing incredibly capable instruction-tuned models every single week?
They bypass it by taking humans out of the loop almost entirely. They use synthetic data.
AI teaching AI. Here's where it gets really interesting.
It really does.
Let's get into the mechanics of this, because this is where the engineering gets wild.
Yeah.
The notes highlight three specific synthetic data approaches: alpaca, self-instruct, and evil instruct. How do these actually work under the hood?
Let's start with alpaca, because it was a huge catalyst. The team behind alpaca realized they could use a massive, highly capable proprietary model like GPT-3 to generate the training data for a smaller, raw, open source model.
So they wrote a clever prompt asking the large model to generate 52,000 distinct instruction and response pairs.
Exactly. They effectively paid a few $100s in API calls to generate a dataset that would have cost hundreds of thousands of dollars in human labor.
It is literally like using your most senior principal engineer, the one who already knows all the best practices, the architectural patterns, and the company formatting, to write the perfect onboarding guide for the brand new junior developers.
That's a perfect way to look at it.
You capture the senior dev's output and use it to train the new system.
That's a great analogy, but the self-instruct method takes it even further. Self-instruct is about bootstrapping.
Okay, how does that work?
You start with a tiny seed pool of maybe 100 human-written instructions. You feed those to a model and ask it to generate new instructions that are similar in style but different in content. Oh, wow.
Then you use the model again to generate the responses for those new instructions. Finally, you run a filtering pass to remove low-quality or highly similar outputs. You create a self-sustaining data generation pipeline.
That solves the volume problem. But what about the complexity problem? I mean, if we are just bootstrapping from simple seeds, don't we just end up with 50,000 slightly different ways of asking, what is the capital of France? Or how do I write a basic for loop?
That's a very real risk.
So how do we get the synthetic data to be complex enough to train a truly advanced coding assistant?
That is the exact problem Evil Instruct was designed to solve. Evil Instruct introduces mathematical mutation to the prompts.
Like genetic algorithms.
Very similar conceptually. It takes a simple starting instruction and applies specific mutation strategies to evolve it into something harder.
Oh, that's brilliant. Yeah, there's in-depth evolving, where it might take a prompt like, write a Python function to sort a list, and mutate it by adding constraints, like write a Python function to sort a list, but you cannot use built-in sorting methods, and it must achieve O of n log n time complexity.
That is so cool.
It also uses broadening evolving, where it mutates a highly specific prompt into a more generalized architectural question.
So by iteratively running these mutations through an LLM, you algorithmically generate a data set that covers an incredibly wide spectrum of difficulty.
Exactly. You get the simple questions, but you also get the complex, multi-constraint, senior-level engineering questions.
And if we connect this to the bigger picture, the democratization of open source AI is heavily reliant on this synthetic data pipeline.
Oh, entirely.
Huh.
Before Alpaca and Evil Instruct, the moat around high-quality AI wasn't just algorithms, it was human data labeling.
Right. The tech giants could afford armies of human contractors. Open source couldn't compete.
But by leveraging synthetic generation, an indie developer can spin up a custom dataset over the weekend for the cost of a few API credits. It leveled the playing field overnight.
It is a massive accelerant, but it also introduces a dangerous illusion.
Which brings us to the reality check.
Yeah. So what does this all mean? With Foscan's transfer learning, Lima's proof that you only need a little data, and synthetic pipelines generating that data for pennies, it's very easy for the developer listening tonight to view instruction tuning as a silver bullet.
It is, but we need to be incredibly precise about what instruction tuning cannot do.
Let's lay it out.
It's critical to understand the boundaries. Instruction tuning is a necessary step, but it's an entirely insufficient step for building reliable AI on its own.
Right.
Instruction tuning absolutely does not add new knowledge to the model, it does not cure hallucinations, and it fundamentally does not guarantee safety.
Let's dive into the architectural reasons why. We touched on the superficial alignment hypothesis earlier.
Yeah.
If we conceptualize the LLM stack using standard software architecture terms, instruction tuning is purely the UI layer. It's a presentation layer. It is not the database.
That is exactly the right mental model. The database, the latent space containing facts, logic, world history, and coding syntax, is compiled during that massive pre-training phase.
And instruction tuning just modifies the loss function over the response tokens to teach the model how to present that data. It teaches the UI.
Exactly. So if the base model didn't read the documentation for a brand new obscure Rust library during its pre-training phase 6 months ago, running it through an instruction tuning pipeline today won't magically inject that knowledge.
You can't tune what isn't there.
You can't pull knowledge out of thin air. In that scenario, the instruction tuning will simply dictate the model's behavior when faced with an unknown.
Because you trained it to be a helpful assistant, it might learn to politely apologize for not knowing.
But far more commonly, the drive to be helpful overrides everything else, and it will politely and beautifully hallucinate an answer.
And this is where the danger really lies for software engineers. Because the model learned the meta skill of following formatting instructions, it knows exactly what a helpful coding response looks like.
It lacks the underlying factual data for your obscure library, but it knows you want code.
So it generates a completely fictional function. The syntax is perfectly indented. The comments are flawless. The variable names follow best practices. And the tone of the explanation is incredibly confident.
It is the polite liar. It acts like a senior developer, even when the logic it's outputting is entirely fabricated.
And regarding safety, it operates on the exact same principle. You can instruction tune a model to refuse certain malicious prompts.
You can train it to say, I cannot fulfill this request when asked to generate a SQL injection payload.
But you aren't actually deleting the knowledge of SQL injections from the base model's weights. The data is still in the database. You just put a superficial block in the UI layer.
And as every engineer knows, client-side validation or presentation layer blocks can always be bypassed.
That's why jailbreaks exist. Prompt engineering can twist the input in a way that slips past the instruction-tuned safety wrapper and accesses the latent knowledge underneath.
Right, instruction tuning sets the baseline for user interaction, but it absolutely does not solve the fundamental architectural challenges of truthfulness and robustness.
Man, that is a sobering but deeply necessary technical grounding for anyone integrating these APIs into their production code base tonight. It really frames exactly what we're dealing with.
It does.
We've unpacked the entire journey from raw text engine to helpful assistant. We've looked at how LLM leverages task diversity to teach the meta skill of instruction following.
And we explored the superficial alignment hypothesis behind Lima, proving that a stylistic UI wrapper only needs a small amount of pristine data.
We broke down the mechanics of synthetic pipelines like self-instruct and evil instruct, mutating prompts to bypass human labor. And we just grounded ourselves with the hard reality of what the presentation layer cannot fix.
It's a phenomenal foundation for understanding the current state of applied AI. But, the engineering challenges don't stop at the UI layer.
No, they don't. Looking ahead at the research, we are about to hit another massive architectural shift. We've spent this entire deep dive figuring out how to make a model generally helpful, a great general-purpose conversationalist.
But what happens when your application needs deep, domain-specific expertise?
Right. General helpfulness won't cut it when you are building an agent to parse complex medical records, analyze tax law, or navigate a massive proprietary enterprise codebase.
Building specialized expertise requires techniques that push far beyond basic instruction response pairs. We have to look at continuous pre-training retrieval augmented generation pipelines and domain-specific alignment.
It requires an entirely different technical approach.
Exactly.
And we're going to dive deep into those exact pipelines next time. But for tonight, as you turn back to your IDE, as you keep building, debugging, and testing, I want to leave you with that paradox we opened with, something to genuinely wrestle with as you interact with these systems.
The double-edged sword of the helpful interface.
Exactly. Because instruction tuning makes a model incredibly polite, highly articulate, and absolutely excellent at following formatting rules. Without actually solving hallucinations or injecting new truth, it essentially acts as the perfect disguise.
It really does.
When it lies to you about a critical vulnerability or fabricates an API endpoint, it doesn't do it with messy, obvious, broken autocomplete text. It does it with perfect confidence, flawless syntax, and the exact tone of a trusted colleague.
Which makes the errors infinitely harder to spot.
Something to keep in mind the next time you hit run on AI-generated code. Thank you for staying up late and diving deep with us tonight. Keep coding, keep building, and we'll catch you next time.